logarithms. Not only for this particular unit, taking square roots, these are going to help you. But when we get into logarithms and we're doing our exponential equations, knowing these perfect powers, knowing these squares and cubes, and continue on with some of these fourth powers for some of the smaller numbers. Powers of 2, powers of 3, powers of 4, powers of 5. To a certain point, I gave you that list and I posted that list exponential chart. The more you know, just without thinking about it, you know your times tables, you know 3 to the 5th is 243. You recognize it. Can you still use a calculator? Yes. But the more you recognize it, the more something, if you recognize that the least common denominator on the problem number 2, on the blue quiz, right now I'm just thinking about, actually on both of them, was 24. Some of you had huge least common denominators, which kind of goes against the word least. The smallest one, because we want small numbers. We don't want to crunch big numbers. The whole point is to make it easier. So when you get such a big number that you're multiplying your fractions by, you might want to ask a question and say, hey, this doesn't seem like what we've been working on, what we've been doing in class. What am I not catching here? So that's got to come up when you're doing these things. I don't recognize something like this, or it doesn't feel right. Not that math cares about your feelings. You might still get to the same answer, but you're dealing with crunching huge numbers. And that's not the point. The point is to make it easier. All right. So obviously the powers of 1 are all going to be 1. 1 squared is 1. 1 to the 3rd is 1. Everything is going to be a 1. However, you realize that, watch this. 1 to the infinity. Literally, it means, I don't know. X equals 10. That's a piece of demonstration. Let me try it. Well, ask a question about things that go to infinity. We can't actually plug in infinity. Infinity is not a number. It's a destination. Okay. Here are my equations. I'm going to type in parentheses 1. Yeah, and just watch. This is just a demonstration. This is not an example. 1 plus 1 over x. And that whole thing to the power of an x. So if I just watch when I plug in 10 by hand, this would be 1 plus 1/10, and then we raise it to the 10th power. 1 plus 1/10 is 1.1 to the power of 10. And then if you plug in 100, that's increasing the exponent, made it a lot bigger. But now this is going to be 1 plus 100 to the 100 power. This is a smaller number. This is 1.01 to the 100 power. 100. So what's happening is inside the parentheses, this is approaching 1. In calculus, when we do these things, they're called limits. It doesn't matter what you get when you plug the number in. What matters is what are you getting as you get close to the number. We can't plug in infinity. But what we're trying to do is we're going to approach it. We're going to plug in bigger and bigger and bigger numbers, and we're going to see what this thing is getting close to as we try to go as far as we can to infinity. Because we can't plug it in. Inside, it's approaching a 1. If I plug in 1,000, this would be 1,000. So 1.001, but now to the 1,000 power. Still far away from infinity, but still getting closer to 1. So to crunch them a little easier, I go to the table and I'll just press 10. And when I punch in 10, I get 2.59. And I go, I'm doing 100. 2.7 got bigger. 1,000. 2.716. 10,000. 2.7181. 100,000. 2.7183, 1 million, so the bigger I make this power, the smaller this decimal gets, the closer this gets to 1, the more this is approaching infinity. This is not going 1 to infinity. It's not even getting close to 1. 1 ain't happening. We're getting some kind of weird number there. $10 million. Now, take a look what this number is. Look, we'll scroll over it. It's 2.71828169255. So we're getting 2.71828169255. So that was 10 million. Let's go to 100 million. See if we have any change in that. A little bit of a change. Just got bigger. 1 billion. I got over here. Say X is approaching infinity. This is approaching 2.71828188271. And this is where I get to introduce myself. Let me introduce myself. I'm Mr. E. That is the number E. And when we get to logarithms, on the calculator, right here where it says ln, natural logarithm, ln, right above it is a little button above the understanding. Right above it, right here, is e to the x power. That e is an actual number, just like pi, talked about it, we did irrational numbers. If I just go e to the first, e to the first power, let's see, 2.71828, 71828, and this thing must round. 7182. As this x approaches, bigger numbers, that eventually will get larger around this up to it. As x approaches infinity, that's the number e. The exact value of it is e, which controls half-time growth, double time growth, or more importantly, compound interest that's compounded continuously, decay, radioactive decay, population growth. It's found in nature all over. And it's a constant, just like pi. Relative to nature, relative to finance. Nobody celebrates E-Day. February 7th, 2.7. E is relative. But it is a limit of this. 1 to the infinity, that's why we call it indeterminate. Because you cannot get to infinity. Who knows what happens there? Because you've never been there. Nobody's been there. So we never assume. 0 to the infinity. 1, indeterminate. Can't assume. Sometimes it might be a 7. It depends upon what happens as you're approaching infinity. Okay? Not on your test, but when we get to logarithms, E will be there. E was even on The Simpsons. Simpsons have provided more math education than most high school programs. Really? Yeah. Seriously. Type in Simpsons math. There's an entire webpage dedicated to how much math is done. Not now. Hey. 2 squared. What's 2 squared? Okay, thank you. 2 to the third. 8. Powers of 2 are going to happen a lot. 2 to the fourth is 6, because you just double. 16, 32, 64, 128, 512, 1,024, 2,048, 4,096, 8,192, 16,384, 32,006. My brain stopped working about Sunday afternoon. 30 squared. 9, 3 to the third. Come on, guys. Okay. You need to know your powers of 3. Okay. 4 squared. 16. 4 to the third. 64. 5 squared. 25. 25. 5 to the third. 125. That's going to come up more than just. There you go. 6 squared. 36. 36. 18. Yes. Then why do people keep putting it? What is 6 to the third? 216. 7 to the second. 49. 49. 7 to the third. 200. 300, or 400, 900.
344.
If you multiply, let's say this is 50, a 50. 7 times 50 is 350, right? But it's not 50, it's one less, so it's 49. I have 49 7, so it's 1 7 less, 343. And I can do 7 times 5, 35. I can do 7 times 50, 350. I can do 1 less than. It's just 1 7 less than. It's just 1 7 less than 57. So I take off the 7 and I get 43. Eight squared.
54.
8 to the third.
500.
512. Because 8 times 6 is 48. 8 times 4 is 32. So 48 and 32. Or 480, because that's in the tens place. Plus 8 is a power 2. So if you know your powers of 2, you know your powers of 8. If you know your powers of 2, you know your powers of 4. If you know your powers of 2, you know your powers of 16. Because 4s are powers of 2, 8s are powers of 2, 16s are powers of 2. So if you know your powers of 2, you know a lot. If you know your powers of 3, you know your powers of 9. Nine squared, 81. 3 to the fourth is 81. Because that's a 3 squared times a 3 squared. That's a 9 times 9. 9 to the third, multiplied by another 9. 9 times, if it was just 80, 9 times 8 is 72. So 9 times 80 is 720, plus an extra 9, 729. This is the easy one. 10 squared has 2 zeros. 10 to the third has 3 zeros. 10 to the fourth, and so on. That's how many zeros you have. If it was a tenth to the first, that's just a tenth, just like anything else. But if it was a tenth squared, then we'll have a calculator. Point 1 is 1 over 10. 1 over 10 squared is 1 over 100. So that must mean it's a 0.01. You move it 2 times. Got 2 decimal places. 1/100th is a penny. 100th of a dollar is a penny. So 2 decimal places. So 0.1 to the third is going to equal a 0, and I'm going to move the decimal place. I'm going to move 1, 2, 3 times. 0.001. It's 1,000. That's your scientific notation. When you're dealing with scientific notation and they give you a number 5.83 times 10 to the fifth, they're saying take this number and you're going to take it 5.83 and you're going to multiply it by 10,000 or so 200,000. You don't want to do that. You just want to take the 5.83 and move the decimal 1, 2, 3, 4, 5 times to the right because that's big. It's positive. You're going to make it bigger. Fill in those empty loops with zeros and you get 583,000. But a negative exponent, 5.83 times 10 to the negative 5 means 5.83. What does a negative exponent do to a base?
Uplifted.
It lifts it. This is 1/10 of the fifth, which means it's 5.83 divided by 10 to the fifth. That's what the scientific notation, oh gosh, it's that rules of exponent crap again he kept talking about. Sorry. It's like, rules of exponents are the key to everything that we do. Negative exponent means this becomes 1/10. So you're just dividing it. And if I'm just dividing by tens, I'm just going to take that 5.83 and I'm going to move the decimal this way 1, 2, 3, 4, 5 times because it's going to get smaller. And I have 0.0000583. Scientific notation. Going into a chemistry class, you got to know which way to move the decimal. Then you got to know how to add, subtract, multiply, and divide with scientific notation. Because we deal with huge numbers and small numbers in chemistry and physics. Next one. Powers of 10. That's the squares here. 11 squared is 121. 12 squared, 144. 13 squared, 169. 14 squared, 196. 15 squared, 225. 16 squared is 56. There we go. 16 is on the list of the twos. 17 squared is 289. 18 squared is 324. 19 squared is, I always messed up this one up. 51 or 61? Yeah. See, I always get that one mixed up in my head. I don't know why. I pause right there. Never trust myself. Because I don't have them memorized. I don't have them memorized. I know them, except I don't know 19 that well. Don't use it a lot. 20 squared is 400. But 20 squared is just this. It's 2 times 10 squared. This is how you do powers of, or multiples of 10 when you got to square them. That's why I put 30, 40, 50, and 800. 2 squared times 10 squared. Again, rules of exponents. So that's 4 and that's 100. 20 squared is just 4 times 100, so it's 400. I don't have to try to go 20 times 20. You can if you want. But you're squaring the 2 and you're squaring the 10 and you're getting 4 times 100. One squared is 421. 22 squared is 440. No. 484. 23 squared is 549. 529. 24 squared is 576. 25 squared is 625. 30 squared is 900. 40 squared is 1600. 50 squared is 2500. And 800 squared would be 64. And if I square 100, I'll have 4 zeros. So 640,000. Yeah.
You got to go.
So, yeah. Thank you. That's what we're going to be doing next. Five 96. When we simplify square roots, there's three things we have to take care of, or any kind of radical. We wrote this up last week. No end roots. Sorry, no end powers left inside of the end root. This is what your quiz is going to be dealing with on Wednesday. So I'm leaving off the word. No perfect end powers left inside of the end root. Perfect end. That means no perfect squares left in the square root, no perfect cubes left in the cube root, no perfect fourth power left in the fourth root. So we want to make sure there's no perfect squares left in this square root. We want to free them from jail. If you know a list of perfect squares, then you try to, what perfect square goes into this. You can try 4, you can try, because 4 is a perfect square. You can try 9, you can try 16. It doesn't end the 5, the 25 is not going to. 36. Now they're starting to get too big. 49 is not going into it. 36 is not going to go into it. But you can try to see if 4 works. You can try to see if 9 is not going to go into it. 16, see if that'll work. Okay. Does 16 work? Well, let's start with 4. This is the square root of 4 times 24. So what you're looking at is this is the square root of 4 times the square root of 24. There's a perfect square. So this is 2 times the square root of 24. And yay, we're done. No, we're not done. No perfect squares left in the square root. So now, did you finish the square root of 24? No. Because that can be 2 times. This is the square root. That's another 4 in there. 4 times the 6. So that's 2 times the square root of another 4 times the square root of a 6. That other 4, that's a 2 times 2. And then your square root of 6. 2 times 2, that gives you 4 square root 6. That's what this equals. Find a bigger perfect square to start the process. We picked 4. 4 is kind of small. Maybe there's a bigger perfect square that we could have used. Well, again, 9, 5 is not going to go. 6, let's try 36. No, 36 is not going to go. 16. 8 is not a perfect square. We want to try a perfect square. Maybe I can divide by 8, but I can't take it out. Square root of 8 does not come out. I want to break it up into perfect squares. So square root 96 can be written as the square root of 16 times 6. 16 times 6 is, and that was actually part of the quiz. I think one of the quizzes had simplify 96 over 32 or 48. It was 96 over 40. No, it wasn't 40. It was 32. It was 96 over 32. And this is 16 times 6. And this is 16. No, it wasn't 16. I can't remember what the heck it was. It was 16 times 6. And then it was 18. And then there was 3 times 6. There we go. And you could reduce that 6. And so the y-intercept was 16 over 3. This is now the square root of 16 times 6. Square root of 16, square root of 6, my bad. Square root of 16 is 4. There's my 4 square root of 6. All of that is predicated on you knowing perfect squares and knowing which perfect squares to factor out. But if you don't know your perfect square, then know how to factor it. And whittle it down. And I did talk about this one last thing before we move on. Talk about this on Wednesday. Break them out of jail. I don't know any perfect squares. I've never been introduced formally. So break it down somehow. Give me a number that goes into 96 even. First thing, get that done. What times what? Good, 2. Thank you. Appreciate your participation. This is 2 times.
46.
40 something. Yeah. Okay. Neither one of those is a perfect square, so you keep going. Have you heard of a factor tree? You never heard of a factor tree. Well, what we're doing is we're making a factor tree. We're factoring one step at a time, just breaking it down into what makes this. What makes it with these branches. Now, as you make a factor tree, bring the branches down evenly. Don't leave any branches hanging. This 2, come on down. And let's just say we keep going with 2s. That's a 2 times a 24. That's a 2. That's a 2. This is 2 times 12. There's a 2. There's a 2. There's a 2. That's a 2 times 6. There's a 2. There's a 2. There's a 2. There's a 2. There's a 2 times 3. When you use this jail method, the goal is to break out of jail, to escape. Here's how it works. 2 guys or girls or whatever breaking out of jail, they need a pair to break out. As they're trying to escape, going over the wall, one of them is going to get shot and killed. Only one of them is going to make it out alive. I know this is a horrible story. Kind of like Cool Hand Luke. Only Luke makes it out. Then he ends up getting killed. I just gave it away. So spoilers on a 60-year-old movie. 2. They make a run for it. Only 1 2 makes it out. Here's another pair of 2s. They make a run for it. Only 1 2 makes it out. So here's the 2 2s that make it out. Here's a 2. Here's a 3. They're not the same kind, so they don't get to make a break for it. So they go back in their square root jail. Whenever breaks out, when they meet up outside, you're going to multiply them back together. Whatever goes back in jail, you're going to multiply them back together. So we have a 4 that broke out nicely and a 6 back in jail. 4 square root 6. And it doesn't matter what I start this factor tree with. You said 8 earlier. This is 8 times 12. Well, 8 times 12, that is a 2 times 4, and 12 is a 4 times a 3. Well, take a look. Here's a pair of 4s. They make a run for it. We have a 4 that escapes. We have a 2 and a 3 that cannot pair up with anybody. They go back in jail. 2 times 3. There's a 6 back. There it is. So you don't have to break the tree all the way down to only prime numbers. You just need a pair. That's one way, or another way to simplify radicals, simplify square root. Now, if they really do something wrong, they get put in cube root jail. Cube root jail is the tougher jail to escape from. You need three of a kind to make a break for it. You need three of a kind to try. So if you don't know perfect cubes right off the bat, then it's kind of tough. So you start with something that you do know. Well, let's start with 8 times 12. So then there's our 2 times 4, and there's our 4 times 3. So there's our 2 times 2, there's a 2 times 2, and there's our 3. These 3 2s make a run for it. In cube root jail, as they're going over the wall, 2 of them are going to get shot and killed, and only 1's going to make it out alive. In this jail scenario, only 1 ever makes it out. Only 1 ever survives. Okay. So these 3 2s make a run. Only 1 of the 2s makes it out. There's not 3 of a kind here. So everybody here goes back in their cube root jail cell. Is back in the cube root cell. So the 2 times 2 is 4, and 4 times 3, there's a 12 back in that jail cell. Which is kind of important as you take a look at what did break out. The 2 that came out and broke out right here came right from the 8, because 8 is a perfect cube, 2 to the 3rd. So when you're dealing with perfect, cube roots, you're going hunting for perfect cubes. 8 is a perfect cube. 8's a perfect cube, 64 is a perfect cube, 125 is a perfect cube, 216, 343, 512, those are the perfect cubes. If you don't know them by heart, then you got to break them down, piece by piece, and find enough factors that can break down. That's how you simplify radical. Also, going back, because we're going to pick up where we left off last week, what is the square root of 3 plus the square root of 2? Wait, let me change that. Let me change that. It's the square root of 9 plus the square root of 16.
What's up?
Yeah, what does it equal?
Oh, 7.
That's 7. Does it equal? Actually, then I'm going to ask this question. So that's a 7. What is the square root of 2 plus the square root of 3?
Five.
Square root of 5. Okay, good. I'm glad you gave me that. Thank you for playing.
Probably.
Well, 50% because you got one of them right. And you have to go back to go because you took the other one forward to go. The first one. Why is this not the square root of 25 using the same logic you did over here? Over here, you went ahead and did 2 and a 3, add them up in here, and that's how you get your square root of 5. Well, shouldn't the same logic apply to this? 9 plus the 16 and square root of 25. What's square root of 25?
5.
Why doesn't it equal 5 instead of 7? Well, yeah, because this obviously is a 3, and that's obviously a 4, and this obviously a 7, right? Well, why, how come, with this, well, how come I can't do it? How come this is not the same? Because that's wrong. That's horribly wrong. Square root 2 is approximately 1.414. This is approximately 1.732. Last time I checked, that does not equal this, which is square root 5. You punch it out, equals 72. 2.71 something. Because that adds up to more than 3. You cannot add radicals 5 plus square root 3 and get square root 8. You cannot add them. It's like trying to add an x plus a y. They're not the same kind of thing. When you add and subtract radicals, you treat them like variables. They have to be the same kind of radical. If I have square root 5 plus square root 5, that is equal to 2 square root 5. It's like saying I have 1 square root 5 plus another square root 5, that's 2 square root 5s. Okay? You do not add the insides or subtract the insides. You don't do anything addition subtraction to the insides when you're doing this. You just combine them like you're going 5 square root 11, take away 2 square root 11. 5 of them, take away 2 of them, just leaves 3 square root 11, just like if you had 5x minus 2x. That's equal to 3x's. The same kind of rule you apply. When you say it to yourself and you're doing the problem, 5 of these square root 11 minus 2 of these square root 11. 5 of them, take away 2 of them is 3 of them. You're combined, they're quantities of them. Those are coefficients. 5 of these minus 2 of those is equal to 3 of them. 9 square root 2 minus square root 2. What's that?
9.
Okay. So far, I haven't heard the answer. What is 9x minus x? 8x. So what is 9 square root 2 minus square root 2? 8 square root 2. 9 of these square root 2 minus 1 of those square root 2 leaves 8 of those square root 2s. And then minus 1 of them. And then, one more before break. Not like radicals. Like terms, these are not like radicals. Maybe you want to say the same thing. They're not like terms, they're not like radicals. So you have to simplify first. Square root of 8 can simplify. There's a perfect square stuck in that square root. Okay. The 3 in front, sticking with the jail analogy. This 3 is the getaway car waiting outside to see who's going to break out of square root 8j. From now on, and I'm going to have to say this again at 10 o'clock, from now on, we need to remember that 8 is 2 times 4, but then the 4 is going to be 2 times 2. From now on, we're just going to go with 8 is 2 times 2 times 2. So it's going to be 2 to the third. Just saves time. So square root of 8, there's a pair of 2's. So a 2 is going to escape. And there's a 2 that's going to go back in square root j.
And then you have, that's simplified, nothing's breaking out of square root two because you can't factor. Plus 4 square root 2. 3 times 2 square root 2 is 6 square root 2. This isn't exactly like saying, what if I had 3 times 2x? That is 6x. You multiply 3 times the coefficient. Multiply 3 times the 2. That's 6 of those square root 2's. So now 6 of them plus 4 of them gives you 10 of those square root 2's.
We're coming back again.